Alright guys, if you haven't done question 1, I know most of you have done question 1 already, so let me do this if you haven't done it. I mean, okay, now you've got three IID observations from a normal distribution with these parameters, and you have two possible estimators for mu. This is the first one. The second one is so these are two possible estimators. So the question is to see which one is better and why, right? Remember, there are two criteria you need to look at. One is the bias, the second is the MSE. So let's look at bias first. The bias, so I'm going to compute the bias of mu1 hat and the bias of mu2 hat. This, by definition, is the definition of bias, as you know, and this is equal to this. Taking the constant 4 outside, inside the brackets you have the expectation of x1 2 times the expectation of x2 plus the expectation of x3. Yeah. Now each of these expectations is equal to mu because of this assumption, right? So this would be quarter times mu plus 2 mu plus mu minus mu, which is equal to 0, of course. So the bias of the first estimator is 0, which is a good thing. All right. Now let's do the same for the second estimator. So you follow the same procedure to find the bias of the second estimator, and you get a third of mu plus mu plus mu minus mu, which is again, sorry guys, which is again 0. So in terms of bias, both estimators have bias equal to 0, and therefore you cannot distinguish the two estimators with respect to bias, right? So what's the next thing you need to do is to consider the MSE. All right, that's what I'm going to. So I'm going to compute now. Start with the MSE of the first estimator. Sorry guys. So I'm going to start with the MSE of the first estimator. Remember, if an estimator has bias equal to 0, then the MSE is the same as the variance. I mean, I proved this in the class, guys, some time ago, right? And so this is the variance of this. Now, if you take the 4 outside the variance, it becomes 16th. Yeah. So you see, the 2 becomes a 4, and the 4 becomes 16, right? Now we know that each of these variances, this one, and this one, is equal to sigma squared, because you're told that each has a normal distribution with variance sigma squared. So this is sigma squared plus 4 sigma squared plus sigma squared, and this simplifies to 3 sigma squared by 8. So this is the MSE of the first estimator, right? And similarly, the MSC of the second estimator can be worked out as follows. Right? The 3 becomes a 9 because when you take outside you have to square it, as you know. So this is 1/9 sigma squared plus sigma squared plus sigma squared, which is sigma squared by 3. Right? Okay, guys. So now, remember what I told you last week. If you have two estimators, you prefer the estimator that has a smaller MSC. Right? So of these two numbers, this one and this one, which one is smaller? This one or this one? The second one is smaller, of course. Sigma squared by 3 is less than 3 sigma squared by 8. And therefore, mu2 hat is the better estimator. Okay? Is that clear, guys? Yeah? I know most of you have done this anyway, so I just wanted to do it. Yeah. Okay. Can you do the question 2, please, now? no, it's outside the sum. So this you mean this one?
Yeah.
Yeah, it's outside the sum.
All right.
Yeah. Alright guys, listen, if you haven't done it, I know some of you have already done question 2, but if you haven't done it, could you please listen guys. The first part is to show that this estimator of mu is unbiased. So to show that something is unbiased, you need to find the bias of it and show that the bias is equal to 0, right? So that's what I'm going to do guys now. I'm going to show that the bias of this estimator is 0, right? So the bias, as you know, is defined as this is the definition of bias. Taking the expectation inside, you have this. Now we know that each xi has a normal distribution, so the expectation of xi is mu. So this becomes the sum yes, you follow? Now because mu is a constant, you can pull it outside the sum, so it becomes mu times the sum minus mu. Yes? Now mu is a common factor, so taking this as the common factor, we have in brackets yes. So this is the bias. The only way that this bias can be 0, is yeah, you follow what I've done. This is the bias, and the only way it can be 0 is if and only if the sum of AI is equal to 1. Alright, so that proves the first part of the question. I know most of you have done this, okay. Is that clear guys? Yeah? That proves the first part of question 2. Now the second part of question 2 is to find is to minimize the variance. So as a first step, let's find the variance. The variance of this guy. If you take the variance inside the brackets, you will have the AI will become squared, right, times the variance of xi. Now we know that each xi has a normal distribution with variance sigma squared. So each of these guys is equal to sigma squared. Now sigma squared is a constant, so you can pull it outside the summation. Yeah. So this is what we get. Right now, if you look at the question, guys, you have in front of you, there's a hint for this question. I'm going to use the hint without proving it, because if I start proving the hint, it will take a while. So I don't expect you to prove it. If you can prove, that's great, but I don't expect you to prove it. I'm going to use the hint, right, to say that we can write this guy here as the 1 over n is outside the summation, right? So you can write this by the hint. This can be written like this. Now we want to minimize this expression with respect to AI. Now there is the only of these two terms. Only this term depends on AI. This is a constant. 1 over n is a constant, so you don't need to bother about it. So you only need to bother about this term. Now what you have here is, if you look at closely, what you have here is a sum of squares of numbers, right? The square of any number must be non-negative, right? And if you take the sum of it, it's also non-negative, right? So the minimum, because we are trying to minimize this whole expression, in particular this, the minimum possible value, the value of this is equal to, will be equal to what? It will be equal to 0. The minimum possible value of this term is 0. Yeah, and that will happen. That is, this whole thing will be equal to 0 if and only if AI minus 1 over n squared equal to 0 for every I. And if this will happen if and only if AI minus 1 over n is equal to 0 for every I. And this will happen if and only if that AI is equal to 1 over n for every I. Hence, to answer the question, the variance is minimized if AI is equal to 1 over n for every I. Is that clear, guys? Yeah. Any questions, guys? Yeah. I mean, if you want, you can prove the hint. It's not very difficult, but it takes me more time. So, you guys agree with that? Yeah. When you do question 3, guys. Also, in question 3, please try to use the hint to make your life a lot easier. You use the hint. Alright guys, alright, so you have xi id normal, and s squared is a possible estimator for sigma squared. Alright, the first they want you to find the expected value of s squared, right, which is, now as I said, you should try to use the hint if you can, otherwise things will be very difficult. Well, you can do it without using the hint, but it will be pretty lengthy. So what I will do is, to make this look like the hint, you see what I've done here. I have multiplied by n minus 1 and divided by n minus 1. I have divided by sigma squared and multiplied by sigma squared. So I haven't changed anything really. And the reason I'm doing this is because I want to use the hint. Alright, now this being a constant, you can pull it outside, so it becomes like this. Yeah. Now this, by the hint, by using the hint, this is the same as a chi-squared variable with n minus 1 degree of freedom. Now, some of you might have done the chi-square distribution before, but we will do that. We will cover that later on in this course, what a chi-square distribution is. And one of the properties I will talk about later on in the course is the following: is if you look at page if you look at page 16 of the notes, you will see that the expected value of a chi-squared variable is equal to the degree of freedom. So in this case, the expected value of a chi-squared variable with n minus 1 degree of freedom is equal to n minus 1. That's the property on page 16 of the notes, right? So the n minus 1 and the n minus 1 cancel out, so you get sigma squared, right? So therefore the bias of S squared, which is the expectation of S squared minus sigma squared, is equal to sigma squared minus sigma squared equal to 0. So in other, S squared is an unbiased estimator for sigma squared. So that's the first part. The second part is to find the variance. Remember, since S squared is unbiased, variance is the same as the MSE, right? So to find the variance, I'm going to apply the same trick, guys. I'm going to write S squared like this. You should know why I'm doing this. You guys understand why I'm doing this? Is because I want to use the hint one more time, right? I have multiplied by n minus 1 and divided by the same thing, divided by sigma squared and multiplied by the same thing. All right, now I'm going to take this constant outside the, sorry guys, this is variance, not, I'm going to take this constant outside the brackets. Now remember, when you pull something outside the variance, you need to square it. So this becomes the variance okay. Now by the hint, one more time, this is the variance of a chi-squared variable with n minus 1 degree of freedom. Okay, and this, we should look at page, I know we haven't done this yet, we should look at page 17 of the notes. You will see there is a formula there which tells you that the variance of a chi-squared variable is equal to 2 times the degree of freedom. So in this case, the variance of a chi-squared variable with n minus 1 degree of freedom is equal to 2 times n minus 1. If you look at this page, guys, you see that. So this is 2 times sigma to the power 4 divided by n minus 1, and this approaches 0 as n approaches infinity. Hence, S squared is unbiased. It's an unbiased estimator because the bias is 0, and consistent estimator. Consistent because the MSC, which is the same as the variance, approaches 0 as n approaches infinity. Okay, guys. These are for you guys. So you see it's a lot easier if you use the hint. Otherwise, you keep going like this. You now do question 4, guys. How do you know this is equal to this? This is slow. This is not the same as this. No, this is a sample mean. This is a x bar is a sample mean. Whereas this is a population mean. So they're two different things. This is population mean. This is a sample mean. All right, guys. Let me show you how to do question 4, part 1. Okay. You are asked to show that gamma hat is an unbiased estimator for gamma, right? So obviously what you need to look at is the bias. You need to look at the bias of gamma hat, which is the expectation of gamma hat minus gamma, which is the expectation of minus gamma. All right, and you should take the expectation inside. You get this, guys. Now, to find the expectation of xi squared, what do you guys do? You are given a PDF, so what do you need to do, guys? You need to integrate. You need to integrate, exactly. So this is, so you need to find this guy, just simply integrate from 0 to infinity of x squared times the PDF, which is given in the question, as x divided by gamma times yes? Are you guys with me so far? Yeah. Alright, now you can pull the gamma outside, so this becomes 2 Any ideas how you can integrate this, guys? What's the best way about going about integrating this, guys? I know the best way is to make a substitution. Is to make the following substitution, that y equal to x squared by 2 gamma s, right? So that would imply that x is equal to 2 gamma y square root, and dx by dy will be gamma over 2y square root. Alright, so put this in a box, guys. Right, and then sub this back into this. You get 2n gamma sum from 1 to n 0 to infinity. X cubed will become 2 gamma y power 3 over 2, and then this will become this, and dx will become gamma over 2y dy. Alright, now I run out of time. You should simplify this. After a few steps you will get this equal to 0, but I'm sure to simplify this you need to use the definition of the gamma function, which I talked about a week or so ago. You remember the gamma function I talked about in the class? Yeah, you already forgot about. I'm sure you do. You need to simplify this. You need to use the definition. So use the definition of gamma function, which I talked about in the class, guys, some time ago. Right, and eventually you will get that down to 0, guys. Okay. If you can't, just come. If you have problems, just see me in person. I'll send you an email, guys. All right, guys. So I'll see you guys next week. Have a good break. Weekend. Have a good weekend. If you have any questions, just send me an email, guys.
It's too crazy.
Your shoes are on.
Hmm?